Welcome. Over the past few months, I have been teaching 5th and 6th graders an enriched math course. As an experiment in this course, I tried to teach them material that is worthy of college. And the problem that I chose was one that I could not solve while still in college and even in graduate school. It was sometime after that I was able to solve this problem. However, with much work and interaction with the students, I found a way to present it so that 5th and 6th graders could show a capability similar to that of college students. The purpose of this video is for my students who have taken the course that they can continue reviewing it after the course is over, and for other students who might want to try to do the same feat that they have done. So let us begin, and we're going to go through a series of slides which show how this work was presented, and at some point in time you can contact the Math and Physics Exploration to get copies of these slides so that you can look at it in more detail than you may be able to see on the video. So let's get started. So this is an outline of what we are going to try to do in the next 6 or 7 slides. We basically want to start off proving the trigonometric identities by multiplying power series for the sine and cosine. That's a statement in itself. To do this, we prepare for the problem by doing the binomial expansion, which is a simpler form of the problem that we're going to try to do. But in order to do the binomial expansion, the student has had to learn the distributive property, which is very key in this. They have to know about the rules for exponents, and they have to know something a little bit about factorials. We will cover some of that later on in the lesson. Okay, to start the problem, we will multiply the infinite power series using the distributive property. In order to be able to do that, one has to know how to multiply fractions, the rules for multiplying by negative numbers, but most key of all, they have to know how to lay the problem out, because that is what gives us insight to the problem and sees the techniques that we need to do in order to solve it. And finally, we collect the information from the distributive property and put it in a form that we can then later use to solve the problem. Step number 3. This was the key. This is the thing that took me years before I could find a solution to the problem. I had to find out and understand the Pascal Triangle and its subtleties a little bit better, and then to be able to explain patterns. And then, of course, finally we use all of this information, which basically involves the transitive property, replacing those patterns with something that are more useful. So let us begin. So we begin our problem by looking at the binomial expansion, which is basically taking an expression a plus b and multiplying it by itself. And basically all we're doing is the distributive property. First we multiply the a times a, giving us a squared, the a times the b, which gives us ab. We continue by multiplying the b times the a, which gives us ba. Using the commutative property, we put it down as ab, and b times b is b squared. Since we multiplied a plus b times itself, that's actually a plus b squared is another way of writing it. When we add the terms from the distributive property, we finally get a squared. We have one ab here and one ab. It gives us 2 ab's plus the b squared. Now we multiply that by ab, which will now give us ab multiplied by itself 3 times. We go through the same process, multiplying a times each one of these numbers, then b times each one of these numbers to get the next line. What is very key in this process is the fact that we've now shifted them over, lining up parameters so that we can use the distributive property to add these together. So we finally get a plus b cubed is equal to a cubed plus 3a squared b plus 3ab squared plus b cubed, noticing the property that the coefficients decrease, 3, 2, 1, no a. And if we were to add up the exponents, we would find that they all add up to 3. Now it turns out when we work with the Pascal Triangle and factorials, we're going to find that we can replace the 1 by 3 factorial over 3 factorial 0 factorial, both for the a and the b. And that for the 3, we can replace that by 3 factorial over 2 factorial, 1 factorial. And once we do that, we can now divide by 3 factorial, which gives us the expression a plus cubed over 3 factorial. And it gives us each one of these terms, which we can find easily, a cubed plus times b0, divided by 3 factorial, which matches the exponent of the a, and 0 factorial, which matches the exponent of b. This gives us an easy way to remember this so that we don't have to memorize it. So this basic setup, once we learn to master this, and I've had children in 3rd grade that have been able to master this fairly easily, that we're now all set to do the problem that we set out to do. But let's do a little bit more to build up to that. So now we start our problem. S of x is a function, which we will later on will find out is the sine function, and it's represented by a power series. And we'll notice a pattern. X to the first power divided by 1 factorial minus x cubed divided by 3 factor, and so on. So we see that we're doing odd powers of x, and then we're alternating the signs from plus, minus, plus, etc. And these series go on forever. So the next term would be x to the 7th 5 factorial. Okay, so then we multiply it by s of x again, remembering that the way we evaluate this function is we pick a particular value for x and place it in every place. So if we wanted the sine of 0.1 in radians, we would put 0.1 for this x divided by 1 factorial, 0.1 multiplied by itself 3 times, divided by 3 factorial, and so on, and then we could find from that series what the sine of 0.1 is. But now let's begin the process. We know that we're going to multiply each one of these terms by that line. So what I've done, since we've only shown 3 terms of the whole expression, I put that line down 3 times. However, on the second one, we change the signs, because a negative number times a positive number is a negative number, and a negative number times a negative number is a positive number. Essentially, multiplying by a negative number changes the sign. Okay, so we've now shown what we've done here, and this is the same thing now, except the first line is multiplied by x1, and we can see that over 1 factorial, and we see that in each one of the terms, going on indefinitely. The next one is multiplied by x cubed over 3 factorial. We see that repeated several times, going on forever. The next line is multiplied by x to the 5th divided by factorial. Okay, and if we were to go to another line, it would be x to the 7th divided by 7 factorial, a negative one, which would start changing signs again. Okay, so that's basically the same thing as we did with the binomial expansion, except more terms, and we had negative numbers in there. But again, notice the displacement of each line, because we want to get them to line up. So now to get the answer, x1 times x1, we add exponents is x squared. Okay, with the 1 over 1 factorial being multiplied. The next term, the x cubed times x1, is x to the 4th power. And we basically use the distributive property to factor that out, and that gives us 1 over 1 factorial 3 factorial plus 3 factorial times 1 factorial. And we do this same thing with the next sign, except these are all plus, these are all minus. And this time we get 3 terms. Now, we would continue dropping this line down or putting this at an angle, because we're now going to get 4 terms, 5 terms, 6 terms, etc. as we do our multiplication. We also notice pattern-wise that we get even powers of exponents. X squared, x 4th, x 6th, the next would be x 8th. But at this point in time, this is where I got stuck in the problem. And this is the key to solving lots of problems. Sometimes you see something and you don't know what to do with it. So since I was working with factorials, I recognized that I have to go back and look at factorials and try to understand them better. And once I do that, I can put in some things that will really simplify this slide. So now let's go to the next slide. The Pascal triangle is going to be key to our solution. Normally this Pascal triangle starts off with the number 1, 0, 0, 0, and we get each line by adding the number that's above it and the number to the left. So if we pick, say, 3, 3 is 2 plus 1, 3 is 1 plus 2, and 1 would be 1 plus nothing else there would be 1. Take the 6, 3 plus 3. So that's how we get our numbers in the Pascal triangle. Turns out those numbers are used in the binomial expansion. But an interesting property which I discovered by playing around with this is that these numbers add up to powers of 2. 1 plus 1 is 2, 1 plus 4 plus 6 plus 4 plus 1 is 16. And we can write these as 2 to the first, 2 to the second, so on down the line. So now I'm going to take every other number. And what I notice is 1, 6, 1, and 4 plus 4 both add up to 8, which is half of what the total sum is. So 8 is 2 to the third, and 16 divided by 2 is 8. So it's important to get it in a form or a pattern that is going to be very useful. Now, the next step we did is we wrote this line in factorials, because this particular line we're going to be used later on. So what I did is, this can be represented by 4 factorial over 4 factorial times 0 factorial for the 1, for the 4, for the 6, for the 4, and the 1. Now, I assume that you would know factorials. A 4 factorial means 4 times 3 times 2 times 1. A 3 factorial is 3 times 2 times 1. And a 1 factorial would be 1. We would have to prove that 0 factorial is 1, but I don't want to distract too much further from the lesson. Okay, so now if we take these alternate terms and replace the 161 and the 444 by its equivalent factorials, we can then divide by 4 factorial. We're basically using the transitive property, or not the distributive property, to factor these out. And so now this becomes, without the 4 factorial, 1 over 4 factorial, 0 factorial, etc., and then the same thing for the alternate terms, the 4s and the 4s. And this now is 2 to the 4th over 2 divided by 4 factorial. So this is the key line here. This is what ends up helping me solve the problem. It all may look simple once you understand it, but it took a while to try to dig further than I was taught. And this is the secret to the way mathematicians solve problems. That they come across an area that they can't move, realize they have to do a little bit more research, try and fail a couple times until they make a breakthrough, and they may have to do this several times. In this case, we only have to do it once. We now go back to our second slide temporarily. And that is that when we had multiplied these together, we found that this would be s squared as the product, but we now had these terms which we didn't understand. And now from the previous with the factorials, we remember this 1 divided by 1 factorial, 3 factorial, plus etc. was equal to 2 to the 4th. 3 plus 1 is 4, divided by 2 times 4 factorial. Using the same approach, we would find 5 plus 1 is 6, 2 to the 6th power divided by 2 times 6 factorial. And the same thing with this. 1 plus 1 is 2, 2 to the 2nd power divided by 2 times 2 factorial. So now let's change the slide and put up the new slide reflecting that change. So what we see here now is those expressions which I just told you. The x to the 4th times 2 to the 4th over 2 times 4 factorial. But what's interesting, we know that the x's are raised to the same power, so we can associate them and write this as 2x squared instead of x squared times 2, 2x 4th, and 2x 6. And so we have a nice simple pattern that's repeated. Now the next thing we will do is take the cosine function, which is now even powers that x is raised to, and we will do the same thing. But the key thing in this case will be that we will also get similar factorial terms, except they will be the odd or even terms. And when we finish this, we will find out, having done the same work, we will get this as 1 minus 2x squared over 2 times 2 factorial, etc. Noticing now that the similarity between these two, this term is the same as that term except the sign is opposite. This term is the same as that term except the sign is opposite. And when we add equal values with different signs, we get 0. So all of these terms will become 0 except the 1. So when we add sine squared plus the cosine squared, we get 1. On the other hand, if we subtracted them, then subtracting the sign, these now become, the signs change. This becomes negative plus negative. So now these match up with these. And when we add them together, you'll notice this is a half and this is a half. That will become a whole. So this becomes 2x squared over 2 times 2 factorial. And we do the same thing with each of the other terms. The half disappears when we add them up. Okay, and so then, now what's interesting is I made a mistake on this slide. These 2's do not belong here. This should be, because when we add them up, they should have gone out. So this should have been 2x squared over 2 factorial, 2x fourth over 4 factorial, 2x 6 over 6 factorial. Well, look at the definition of the cosine again. 1, x squared over 2 factorial, x fourth over 4 factorial. The only difference is we have 2x instead of x. So since there's a function, we substitute 2x for this, and this would now be equal to the cosine of 2x. So we have now proved 2 trigonometric formulas, and we've also discovered that I made an error in the signs by not leaving these 2's out. Once we have done the sine squared and cosine squared function, this next problem, even though at first glance looks much more complicated, it's not that bad. So this time, since we won't necessarily have the same value for the cosine, we put a y in instead of an x. And so now we're going to multiply the sine by the cosine, and we do as we did before. We copy that line down each time, and then multiply y0 first, which we see here, then multiply by y2 next, which we see here, and multiply by y4 next. And that is done for 3 lines, but as we said before, this would go on indefinitely. Okay, so we're looking at those first 3 lines, and we're going to sum them up. So this represents the sine of x times the sine of y, and what we're doing is we're noticing that when we add the exponents of the different variables, they add up to the same number. 0 plus 1 is 1. Over here, 0 plus 3 is 3. 1 plus 2 is 3. 5 plus 1 is 0. 3 plus 2 is 5. And 1 plus 4 is 5. So we see that they're adding up to odd exponents, even though we don't actually add those exponents. It's just we're noticing that pattern. Now we would like to do the same thing, except for s of y and s of x. Well, all we're doing is placing x where y was and y where x is. So we just take this. So where we had y0, we put an x0. Where we had an x1, we put a y1. Where we had a y0, we put an x0. Where we had an x3, we put a y3. So we don't have to do this work all over again, just recognizing the symmetry in the problem. Now we add these 2 together. And so we're collecting these 2 terms, these 4 terms, these 6 terms. And when we collect them together, what we will notice that these are actually, if we replace the y's and x's by a's and b's, this is what we got when we were doing our binomial expansion before. And so now once we see this, this term can be replaced by x plus y over 1 factorial. This set of numbers can be replaced by x3 divided by 3 factorial, and this by x5 divided by factorial. And once we look at that, we see that that's the same as the sine function. Instead of having x, wherever we have x plus y. So we've now proved that the product of the sine of x times the cosine of y plus the sine of y times the cosine of x is equal to the sine of x plus y. So what we've tried to do is package this in a way that would make it easy to understand. So here was our binomial expansion. Remember, we decided to replace these numbers by the factorials, which we now understand better when we looked at our factorial section. And when we divided by 3 factorial, those were the terms that we had when we were doing the products of the sines and cosines and adding them together. So what we've tried to do is put the problem in a form that is easy to follow and understand. And all it does is take a little practice.